So it's time to introduce the last speaker of this morning session, Géraldine Bouet. She's a lecturer, researcher in food safety, risk assessment, risk-benefit assessment, predictive microbiology, and food processing. Her research activities are mainly risk-benefit assessment in foods, microbiological risk assessment, and predictive microbiology. She's working at SECALIM, a French research unit of INRA, and ONIRIS, the Nantes Atlantic College of Veterinary Medicine, Food Science and Engineering. So please, Géraldine, the floor is yours. Thank you.
Thank you. Thank you, Veronica, for this kind introduction. It's a pleasure to present at the Parma Summer School the result of a novel food risk-benefit assessment. It's the first that was done so far. So let's see what we have done. First, I will describe the model structure for you to see what was considered and how we made the simulation. We will see the food intake that we estimated, the individual risk and benefits that we assessed in nutrition, toxicology, and microbiology. And then we will see the health impact that was estimated before the conclusion. First of all, it was part of the NOV RBA project that was novel food as red meat replacer, an insight using risk-benefit assessment method. It was granted by EFSA as a knowledge exchange grant coordinated by Professor Andronike Naska from NKUA in Greece. And it was a collaborative project also with INRA, my institute in France, in Denmark, Day2, and BFR in Germany. So all of this unit were involved in the project. There is a report available in the EFSA journal where we explain the case study that I will describe now, and also the improvement in terms of method that we have done, and also the communication in risk-benefit. The two last parts are not included here. Regarding the case study, so the objective was first to develop a risk-benefit assessment model to estimate the overall impact of making the substitution of red meat by insect species in burger. So we had to first estimate the consumer exposure in the substitution, and we had a reference scenario with the beef patty burger. And for the insect, the species that was selected is Aceta domesticus powder, because it was one promising spicy end product at the time. And we have developed and implemented a model to have a quantitative risk-benefit assessment. The main output that were targeted, that it was the number of cases per disease that could be prevented or increased by making this food substitution. And this was converted in DALI that you have seen just before. And just to summarize again what is a DALI for people who are not very familiar, one DALI is equivalent to 1 year of perfect health lost. So it's a negative when we count one DALI. And this DALI enables to take into account the quality of life that could be lost. If you see in the scheme in this example, if someone is sick during 20 years, this person could lose half of his quality of life. And we can also count from premature death if you die before your life expectancy. So this enables to compare or to integrate different diseases that will have different effect in terms of mortality and morbidity. So it's an aggregated output. In our model, so we first did a systematic review of all the nutrient and the hazard in terms of microbiology and chemistry that we could have in insect. Insect, as it's a novel food, we didn't have so much data, and we had to explore everything that was available at that time. Whereas for beef, that is a traditional food, we had key review and database reporting this information. And the amount of components to be assessed, you can see, is quite large, more than 70. as we found 41 nutrients, 18 microorganisms, and 14 chemicals. This is what we call a long list identified in the literature of components of interest. Then we have screened and ranked all of these components according to their occurrence and severity. And this enabled to get a short list of components of interest to be included in our quantification. And then for each component, we have analyzed the data that were available in terms of quality to see if it was feasible to make a final estimate in terms of number of cases and value, as mentioned before. And this provided the final list. These are the three lists. So the red one is the one you have seen before. The short list is the component that we would have loved to include, but the final one is what was feasible. And it's very important to keep in mind that when we go for a quantitative risk-benefit assessment, unfortunately, we have to cut the list of components because of availability of data. So the conclusion must be considered also according to this cut. Then for each component, this is how we developed the model. So this is a modular process where for each component, whether it's a nutrient or a chemical or microorganism, we have collected information on the level of this component in beef and in Aceta domesticus, that is mentioned AD in the presentation, powder. And we had this level and also some frequency of contamination for chemical and microorganisms. In parallel, we have also collected the national data for Greece, France, and Denmark in terms of beef consumption in each country, and because we wanted to assess what if we replace this beef by an insect powder. And we have combined both to get some exposure of the reference scenario and the alternative. We have used some dose response, so epidemiological studies for nutritional and chemicals. And for microbiology, we use some source attribution methods, and we use also predictive microbiology. This enabled to estimate the number of cases and the DALI when we move from reference to alternative scenario. The simulation was done using Monte Carlo simulation on at-risk. That's an additional software of Excel, and you can do it also on R. We have included the variability and the uncertainty in the model. For the exposure assessment, to give you some example, we have considered that in a party in each country, there is a varying percentage of pure beef. Some country consume and some consumer pure beef patty, and other ones it's a mix with other ingredients. Also, the individual food intake is varying according to peoples and even countries. The nutritional composition is not a deterministic value also, as well as the concentration and of the hazard in the food. We also had some uncertainty regarding the different dose responses, the incidence of the disease in the country, and the DALI per case. So all of that was implemented with distribution. The scenario that we compared, so the reference scenario is the current situation in each country with the assumption that we have some beef burger containing a pure beef patty, another one a varying composition, and the pure beef part was replaced by a mix of powder with water, because of course it's rehydrated. So we do not compare a pure beef with a powder of insect that you would not consume directly, but a mix. This is the result that we obtained for the food intake of the current situation for beef. So you can see that Greece in red, you have also France in green, and Denmark in blue. We have different amount consumed in each country. So this is important to take into account, as well as the frequency of consumption. For instance, in Greece, every day, 5.9% of the population is eating ground beef. So this is also considered in the model and different between the countries. This is the cumulative distribution, the same figure, but you can see better how it's distributed, and we use this one for making the substitution. And this here you have the insect substitution. So this is a virtual estimate based on the current beef consumption. You see that the amount is very different between the two, beef and insect. It's because the insect powder is rehydrated. The exposure was estimated, so for each country, each scenario, each nutrient. For the nutrient, we had some distribution for the concentration. And what you can see here in a range are the nutrients where when you substitute in your beef, in your patty, the beef by the insect, we increase the exposure to calcium, copper, fiber, magnesium, selenium, and some fatty acid, whereas we decrease the exposure to the blue nutrients that are mentioned here. These nutrients, they were linked to different health outcomes that we found in the literature and where we had some epidemiological dose responses. You can see that some nutrients are associated to the same health outcome. If you look at the calcium, calcium is increasing when we move from beef to insect in patty, and this increase was linked to a potential decrease of breast cancer and colorectal cancer cases, but an increased prostate cancer. Fiber was linked with all the health outcome, and it was decreasing most of the risk. Iron with lung cancer, magnesium with diabetes, sodium mainly with cardiovascular disease, vitamin B12 with two cancer, and zinc. So you see that the picture is quite complex when now you look at all the nutrients. Some increase, other ones decrease. The health outcome, we have different effects, sometimes beneficial and sometimes it's more linked with a risk. So that's why we needed also to have this daily output to be able to make, to see exactly how the overall health impact is beneficial or not. Also, if you look in pink, the data that you have is the mean daily per case. It means that a case of breast cancer in the population is estimated to 2.4 daily. It means in average, people will lose an equivalent to 2.4 perfect years of life. So it's a mean in the population. It depends at which age you get the cancer, but you can see that it's very variable, this severity between the different health outcomes. When we integrate all of this information, I'm going very quickly with the model, but everything is in the report. You can see that the overall impact is a negative DALI. So it means it's a benefit because DALI is negative, and this is valid for the three countries. The main nutrients that are influencing this output is fiber and sodium. For toxicology, only inorganic arsenic in beef was considered, and it's a beneficial effect because by substituting beef by insect, we decrease the exposure to inorganic arsenic and so potentially to bladder, lung, and skin cancer. When making the calculation at the end, you can see that it represents a very small amount of DALI saved. So compared to nutrition, it's very little. In microbiology, so beef and insect can be associated with different hazards, and sometimes the same can be found in both. And you can see here in pink that the severity is varying a lot between, for instance, Listeria monocytogenes, leading to 3.7 DALI per case, and Bacillus cereus cases with less than 0.002 DALI. We had some situation where we have a benefit because toxoplasma here is considered as a benefit because when you do the substitution, you are unable to not have cases of toxoplasma because this was associated only with beef and not insects. So by making this substitution in your food, you decrease your risk to toxoplasma. At the end, the result is also positive in terms of health because the DALI is negative for the 3 countries, mainly due to the decrease of the risk to toxoplasma and a small increase of risk of Bacillus cereus. At the end, the overall change in DALI per 100,000 people in each country, and we put in 100,000 people to get something can compare, is beneficial in each country. Here you have the detail for all of the domain, and you see that nutrition and microbiology are influencing the more this final output. Now, as a main conclusion, first, there were important limitations in our estimate because we have considered only a selection of components, and for instance, in nutrition, there were other nutrients and health outcomes that would need to be considered, but we did not have the data. For microbiology, also, there is a potential concern about Clostridium botulinum. That could be a hazard we could find, but we had any data on it. So it's very important to consider that, of course, if we find more data, we could refine our results. We also had a lot of lack of data for the novel food, of course, because it's not so much consumed. So we could update in the future this value. The recipes also that we used are kind of virtual because it's a product that is not really developed at the moment. So we need to refine the estimate with this information when they will be available. And there were also some lack of information, for instance, for the dose response of the fatty acids and for incidence and DALI for some countries. For the case study, the overall health impact that was estimated is positive at the moment with what we have. So this is a good sign for this novel food. There is a high contribution of the nutritional impact and also for the microbiological ones. And there is some challenge regarding the novel food, and this is valid also for any novel food that you would like to assess, is the lack of data. So, of course, a systematic review approach is needed to capture all the inputs that are available, but also a collection of data would be needed. Also, the conclusion you see are valid at a country scale, because when you do some DALI estimate, you also consider the incidence of the disease in each country, the DALI, and so on. So, and the food intake could vary. So it's important to not do this risk-benefit assessment at a European scale, for instance. And also, in when you do a substitution scenario, it could be interesting to make some survey to see exactly how the consumer will introduce the novel food in their diets. Well, I think that's it for this presentation. The substitution is very key. As mentioned in the previous presentation, if you stop to eat something or if you eat a novel food, this will be in replacement of another food. And it's in this context that it's very important to focus more on substitution in your risk-benefit assessment and not only on a specific food or a specific nutrient. Thank you very much for your attention, and if you have any question, feel free to ask.